Okay guys, today I want to talk about k-permutations of n function in Haskell. You can read about what is k-permutations of n by this link. I do understand what this is. I will give an example. If we have some set of three elements, 1, 2 and 3, we represent our set via list, and we have to choose by two elements. This means that we must produce this list which contain of pairs, because here we have two, and pairs generated in such a way. We take a first element 1, and when we can choose for second element all other elements except this one. So at first we choose 2 and at second we choose 3. Now we choose all of them and we need to take the next element. This is 2, and we can choose all other elements. This is 1 and 3, and so on. We take 3 and choose 1 or 2. So this thing called k-permutations of n. They implement this in Haskell. We start from simple case. We will implement parent function which takes some lists. And for implementation we will use do notation. We know a list is monad, so we can extract every element of this list and bind it to the X name, okay? And I want to generate pairs at first. So the second pair will be Y, and I must generate it from XS minus X. So I need to delete from XS X, and then I need to return a list. Return a list of X and Y. Okay. So let's check how this worked. I will reload my module. It's reloaded, and call our parent function with 1, 2 and 3, and we get expected result. So next thing, let's expand it a little bit. I redefine these functions, the XS, and I define the XS like that. And so for Y, I will call the YS, and this is the XS minus Y, okay? And we can use this monad, this list, to generate a new Z value. So, and we need to return X, Y, X, Y, and Z. So let's reload and call it for 4 elements. And you can see that we got triples here. Okay, this is triples, but this is some corner cases. I need to implement this function for every n, every possible n, 2, 3, or etc. So I can expand this definition. But how can I do this in common case? To do this in common case, we need to use two things. First, monads, and second, recursion. We know that I can rewrite this do notation in with monadic bin function. So let's do this. I will call new function prm, and it take XS, and it take this n, which shows how many elements I need to choose from my initial set. So let's at first let's take our set, and we are going to take every element of this set and of this list and bind every element to the classly function. I will call this element x, and here I need to construct a new monad. Okay, monadic interface of bin dictate me this. Okay, I can get my PRM function. And call it with some. I can, to reduce the task a little bit, I can first of all I can delete x from xs my x, because I don't need it there anymore, and I need to reduce the n-1 because I want to solve task of lower level. So if I want triples here, I need to get all pairs. Okay, and for every of which pair I need to add my x at first to get a triple, and so on. So we somehow reduce our task to lower level task, and from lower level task we reconstruct the solution of our task. So this means that PRM returns me a monad, a list, and I can fmap this list with partially applied const operator constructor. So I just take x and add it to every solution of lower tasks, and that's all. That's solution, I think. It marks to work. Let's try to reload. Yes, let's try to run this on this list with 2 elements. Why this not work? Sorry, of course I need to some corner case here. We always reduce the task and we need to catch the bottom, the lowest level. And the lowest level, if we have some list, no matter no matter what this list is, we must have 0 here. And this in this case we need to produce a list of empty list. So let's reload and let's run, and we can see that we done this. We have all pairs. Of course I can get all triples, and that's all. At the end, let's do some function which generates every k-permutation of n. So by 1, by 2, by 3, and so on for n. So how I will call this function p, and it takes some list xs, and it produce. First of all, we need to take a list from 1 to length xs, and then they need to fmap to this list our PRM function with partly applied xs. And let's see what we will. I don't think this needed here. And let's see what we need, what we have. PV1, 2, 3. Okay, you can see this list of lists, and we need to reduce the level of lists, and better way to do this is use a join function from this module. Let's look at its type signature, do exactly what we want, it reduce some layer of list here. Okay, I use join here, and let's look at our result. 1, 2, 3. Okay, we can see what they get, lists of all possible k combinations. So guys, actually this is one line implementation, 2 lines, okay, but it can be doing 1 line, and I think it's very nice and clean. So thanks for watching, push subscribe button, push like button, and sorry for my English, bye.